Mass spectrometry allows chemists to weigh atoms and molecules not directly on a balance, but by measuring how ions formed from them are accelerated and deflected by electric and sometimes magnetic fields. There are many types of mass spectrometer, but they all work on this basic principle. This instrument is called a magnetic sector instrument. The sample is introduced here, and the positive ions are formed here by bombardment of the sample with a beam of electrons. The ions are then accelerated by an electric field and then deflected in a curve by a further electric field. They then bend through a magnetic field and are further deflected by another electric field here. The ions then enter a detector here. By varying the electric and magnetic fields, ions of different mass can be made to enter the detector. These pumps keep the interior of the instrument under a high vacuum. This is to allow the ions, which are moving at speeds of many kilometers per second, a free path without collisions with air molecules. As the ions are formed from molecules of the sample, they may fall apart or fragment. The ion of largest mass is often the parent or molecular ion, an ionized molecule that is not fragmented. Other peaks of smaller mass may represent charged fragments of this ion. The masses of these fragments may give clues as to the structure of the original molecule. Liquid samples are placed in the tiny sample tube as shown. Here we're running the mass spectrum of limonene, an alkene which can be obtained from the peel of citrus fruits. Only a little is required. Mass spectrometry can detect down to as few as 10 to the minus 12 moles. Volatile samples can be run neat. Less volatile ones are dissolved in a solvent such as dichloromethane, which then evaporates. The sample tube is placed in this probe, which is then inserted into the instrument via an airlock, so that the vacuum in the instrument is maintained. Volatile samples will vaporize at the low pressure inside the instrument, but the probe can be heated to vaporize less volatile ones. The electrons stream out from a heated cathode towards an anode, which is held at a potential of around plus 70 volts relative to the cathode. This is the ionization chamber where the positive ions are formed. These are formed when high-energy electrons strike the sample molecules. You can think of this as the electron beam knocking out an electron from the sample molecule. The sample fits here, and ions pass out through this slit. The heater itself is here. The electrons are accelerating in this direction, and the ions stream in this direction through the slit. The positive ion beam passes between two charged curved plates, which deflect it in a curve so that it enters the area here, where an electromagnet produces a vertical magnetic field. This further deflects the beam in an arc of a circle. On emerging from the magnetic field, the beam is deflected again by another set of charged plates, which direct it into the detector. The amount of deflection by the magnetic field depends on the mass of the ion, strictly its mass-to-charge ratio, but the vast majority of ions have only a single charge. The deflection also depends on the strength of the field. Heavier ions will not be deflected sufficiently in the magnetic field to reach the detector. Lighter ions will be deflected too much. During a run, the magnetic field is gradually increased so that ions of successively greater mass enter the detector. The mass spectrum of limonene looks like this. Each vertical line, called a peak, represents a different ion, and its mass in relative atomic mass units is shown on the horizontal axis. The height of a peak represents the abundance of that ion. The peak at 136 units represents the parent ion, the whole molecule that has lost an electron. The peak at mass 121 units, 136 minus 15, is the parent ion from which one of the CH3 groups, relative molecular mass 15, has broken off in the ionization chamber. And the peak at mass 107, 121 minus 14, could be formed by further loss of a CH2 group. Other peaks are caused by more complex breakdowns and rearrangements. Simple mass spectra show the masses of ions to the nearest whole number, which is fine for many purposes. However, this instrument can display masses to 3 decimal places of an atomic mass unit. This is called a high-resolution spectrum. It enables us to distinguish between different molecular formulae which have the same relative molecular mass to the nearest whole number. Here we see that the relative molecular mass of limonene is 136.125. This means that we can distinguish C10H16 from, say, C9H12O, which would have a relative molecular mass of 136.194 to 3 decimal places. Many mass spectrometers are of desktop size. This one takes in samples from a gas chromatography instrument. As each component comes off the gas chromatography column, it is fed directly into the mass spectrometer. The combined technique is called gas chromatography mass spectrometry, or GCMS. This is the column from the gas chromatograph. This particular mass spectrometer does not use magnetic deflection of the ions. It uses a complex electric field. However, the principle of forming ions from the sample and separating them according to mass underlies all types of mass spectrometer. This is the gas chromatogram of an impure extract of orange zest. The large peak is limonene, and the others represent impurities. Clicking on the peak shows the mass spectrum of limonene.